I'm Dr. Catherine from ChemPraxis. Today we are going to discuss 9701 paper 42 February-March 2024 paper. For the first question, potassium iodide is used as a reagent in both inorganic and organic chemistry. Potassium iodide forms an ionic lattice that is soluble in water. Define enthalpy change of solution. Enthalpy change of solution, the keywords that we are looking for. First one is enthalpy change. 1 mole of a substance dissolve in water. Infinite solution or solution of infinite dilution. These are the keywords that we want. While for the second questions, potassium iodide has a high solubility in water, although its enthalpy change of solution is endothermic. Explain how this high solubility is possible. Usually, if enthalpy change of solution is endothermic, means that you need high energy to break the ionic bond. So, if you need high energy to break the ionic bond, means that they have very strong ionic bonds. They prefer to attract to each other for the oppositely charged ion rather than dissolve in water. So, why high solubility is possible? Because maybe there is a large increase in entropy, so the delta S is positive, and your Gibbs free is negative. Because for the reactions, whether it can happen or not, it's not only depends on enthalpy change, but it also depends on entropy and also temperature. For the next question, table 1.1 gives some data about the halide ions, chloride ion, bromide ion, and iodide ion and their potassium salt. Explain the trend in the enthalpy change of hydration of the halide ion. So for the chloride, bromide, and iodide, as you can see that going down the group, the enthalpy change of hydration decreases, or we can say that they are less exothermic or less negative. While for the explanation, we can say that because the anionic charge density decrease, charge density, we usually refer to charge over the size. So for chloride, bromide, and iodide, they increase in size when you're going down the group. So when you increase in size, then the charge density decrease. And because of that, you will have a weaker ion dipole interaction, means that the attractions between the water and also the halide ions going down the group, they will become weaker. The next one, the enthalpy change of solutions values of this potassium halide are almost constant. Use the enthalpy change of hydration and lattice energy data in table 1.1 to suggest why. Because the difference between lattice energy and hydration energy remains roughly constant. So you can see that this is, if you try to work out the values for these and this and this, you actually will get a roughly similar value. And if you want to calculate enthalpy change of solution, this is the formula that we use. We will minus or reverse lattice energy and then plus the enthalpy change of hydrations. For the next question, the enthalpy change of solutions of potassium iodide is positive 21. Use this information and data in table 1.1 to calculate the enthalpy change of hydration of the potassium ion. This is the formula to calculate enthalpy change of solution. So we have lattice energy, we have the hydration energy of the halide ion. It's just that we need to look for the hydration energy of potassium ion. So with these calculations, you will get negative 315. For the next question, solid lead iodide forms when potassium iodide is mixed with lead ions. The solubility product is 7.1 times 10 to the power of negative 9 at 25 degrees Celsius. Calculate the solubility of lead iodide. So I need the ICE table in which that I need to know what is the solubility, and X represent the solubility. So for change, we always follow the mole ratio. This is 1, so plus X. This is 2, so plus 2X. So this is the equilibrium number of mole or equilibrium concentration. In this case, it's equilibrium concentration. So this is the KSP. We will put this value into this formula, and then we will try to calculate what is X. So after the calculations, we will get 1.21 times 10 to the power of negative 3. And for the next question, the ionic radius of Pb2 plus is 0.12 nanometer compared to 0.133 nanometer for potassium ion. Suggest how the lattice energy of lead iodide differs from the lattice energy of potassium iodide. Explain your answer. So for lattice energy, we usually comparing the charge density and the strength of ionic bond. Since your Pb2 plus has a greater charge and also it is smaller than potassium ion, we actually will say that the Pb2 plus has higher charge density. So there is a greater attractions between Pb2 plus and I minus. So the lattice energy confirmed will be more exothermic. So for question C, potassium iodide slowly oxidizes in air, forming iodine. So this is the chemical equations, and this is the enthalpy change. So calculate the standard entropy change of reaction 1. If you want to calculate standard entropy change, you can use entropy change of product minus entropy change of reactant. So this is the calculations, and this is the final answer. So you need to follow the mole ratio. Don't forget that. So after that, for Roman 2, use your answer to C1 to show the reactions is spontaneous at 298K. As we know that if let's say the reactions, in order to be spontaneous, your Gibbs free energy change need to be 0 or negative. So in order to prove that, we will use the enthalpy change value, and then we will use 298K. Please don't forget to change your entropy from joules to kilojoules. And then you do the calculations. If you get a negative 50.1 kilojoule per mole, means that this reaction is spontaneous or feasible. For question 3, the group 1 carbonates are much more thermally stable than group 2 carbonate. State and explain the trend in the thermal stability of the group 2 carbonate. So first of all, there is increase in thermal stability down the group. The reason is very simple, because the cationic radius increase means that the size of the group 2 ions increase. So you have less polarizations of anion electron cloud or less distortions of carbonate ion electron cloud. And the next one, question D, a student electrolyzes a solution of potassium iodide for 8 minutes using a direct current. The half equations for the reactions that occurs at the anode is given. Write a half equation for the reaction that occurs at the cathode. Include the state symbol. So a lot of students will make a mistakes. They will write the ionic equation for potassium, but this is an aqueous solution. So if let's say this is an aqueous solution, I have two options, potassium and hydrogen ions. I will go with the hydrogen ions because hydrogen ion is less reactive. So you should give me 2H plus bracket AQ plus 2 electron in order to form hydrogen gas. Then we come to questions Roman 2. After the electrolysis, the iodine produced required 21.35 of 0.1 mole per dm cube of sodium thiosulfate to react completely. Calculate the average current used in 8 minutes during the electrolysis. So first of all, we will calculate the number of moles of sodium thiosulfate. So this is the number of mole. And then from the mole ratio in the chemical equations, we will be able to find what is the number of mole of iodine. So we divide 2, and this is the number of mole of iodine. After that, we need to use these half equations because we need to find what is the number of mole of the electrons. So this is the number of mole of electrons, which is 2.135 times 10 to the power of negative 3. And if we able to find the number of mole of electron, we actually can compare to this Faraday constant, in which 1 mole of electrons is equals to 96500 coulomb. We can cross multiply, and then we can get this value. So once you find the value of Q and you have the 8 minutes, please don't forget to convert it to seconds. You can find the current at last. So the current is 0.429 ampere. For question E, potassium iodide is used as a source of iodide ions in organic synthesis. One example of this is shown in the synthetic routes in figure 1.1. So I have A, steps 1, change to NO2. So this is a nitration process. And then from B to C, step 2, you change your NO2 to NH2. So this is a reduction process in which we need tin and concentrated HCl. And we have NaNO2 and HCl for step 3. This is the reagents that we need in order to make benzene diazonium ion. So after that, we have the substitutions reactions in which they substitute benzene diazonium ion with iodide ion. So this is for step 4. So identify the reagents required for step 1 and step 2. We need concentrated nitric acid and concentrated sulfuric acid, and we need tin and concentrated HCl. For the next questions, step 3 occurs in 2 stages. Stage 1, NaNO2 and HCl undergo an acid-base reaction to produce HNO2. Stage 2, HNO2 reacts with C to form D. Complete the equations for stage 1 and stage 2. So NaNO2 plus HCl, they will form HNO2 and NaCl. We call this as a nitrous acid. And then for phenylamine to react with nitrous acid in acidic condition, they will form benzene diazonium ions and water molecule. For Roman 2, the iodide ion from potassium iodide react with D in step 4. The mechanism is shown in figure 1.1. Suggest the name for this mechanism. Since you involve a nucleophile, this is nucleophile with lone pair of electrons, and you substitute your N2 positive to iodine, we call this as a nucleophilic substitutions. For the second question, water is an amphoteric compound that also acts as a good solvent of polar and ionic compound. Equation 1 shows water acting as a Bronsted Lowry acid. Identify the 2 conjugate acid-base pair in equation 1. So for acid 1, it is H2O. And then for conjugate base of acid 1 is OH minus. Means that when you reverse the reaction, this will be a proton acceptor. And then for acid 2, you can use HNO2, and the conjugate base is after they donate the protons. For second question, water also behave as Bronsted Lowry acid when it dissolve CH3 and H2. Explain the ability of CH3 and H2 to act as a base because nitrogen has lone pair of electrons on the nitrogen atom, so they can use this to attract or accept H plus ion. Write an equation to show water acting as a base with CH3COOH. CH3COOH is a weak acid, so when they react with water, they can donate the H plus ion to the water, so water will become H3O plus, and this one will become CH3COO minus. For question B, the ionic products of water Kw measures the extent to which water dissociates. Figure 2.1 shows how Kw varies with temperature. So write an expressions for Kw. Kw is water dissociation constant. We usually use product over reactant. So we will use the H plus ion times the OH minus ion, but we will not over water because water, the concentration is constant. And for question 2, use information from figure 2.1 to deduce whether the dissociation of water is an exothermic or an endothermic process. Explain your answer. As you can see that the Kw increase when temperature increase. So it means that it is an endothermic reaction. And also it means that when the temperature increase, they will shift the equilibrium to the right. Because they shift the equilibrium to the right, so I have higher Kw. And for question Roman 3, an aqueous solution has pH 7 at 30 degrees Celsius. Use information from figure 2.1 to explain why this solution can be considered to be alkaline at 30 degrees Celsius. First of all, we need to find what is the Kw value at 30 degrees Celsius. So from the graph, we can tell that the Kw is equals to 1.5 times 10 to the power of negative 14. And since we know what is the pH, so we can change it to the concentration of H plus ion, and we can use this to calculate the concentration of OH minus. And when you calculate the concentration of OH minus, it is 1.5 times 10 to the power of -7. We can see that the concentration of OH minus is more than the concentration of H plus ion. So that's why we say that this solution is alkaline. For question C, the three physical states of H2O have different standard entropies associated with them. Table 2.1 shows this entropy value. Explain the difference in the entropy value of ice and water. So for water, the particles have more randomness, so that's why they have higher entropy. Explain why the increase in entropy is much greater when water boils than when it melts. Because for gaseous water vapor, they have much more randomness. Yeah, so that is the reason. And for Roman 3, the energy change for ice to water are shown. Use this data to show that the melting point is 0 degrees Celsius. So in order for the reaction to be feasible, the delta G need to be 0. So we put 0 here. And this is 6.03 according to the value given, and we are trying to calculate the temperature. And we need to find the entropy change by using the product, deduct the reactant. So we use 70.1, deduct 48. And don't forget to change it from kilojoule, from joules to kilojoule. So after you do all the calculation, you will find that the temperature is equals to 273 K, which is equals to 0 degrees Celsius. For question D, metal A batteries are electrochemical cells that generate electrical energy from the reaction of metal anodes with air. The standard electrode potentials for the zinc air battery are shown. So this is the half equation, and this is the standard electrode potential. Calculate the standard cell potential of the zinc air battery. Well, we can use this to determine which one is oxidation and which one is reduction. Usually the more negative value will go through oxidation and the more positive value will go through reduction. So we will use E reduction minus E oxidation's formula. We will use 0.4 minus negative 1.22 to get 1.62. And the next question, the zinc air battery usually operates at pH 11 and 298 K. The overall cell potential is dependent on the OH minus concentration. The Nernst equation shows how the electrode potential at the cathode change with OH minus. Calculate the electrode potential. So the first thing, I will try to find what is the pOH. And I can use 14 minus pH to find the pOH value. And after that, this pOH value can be converted into the concentration of OH minus. Well, according to the formula, we are having 2 electrons. So Z is equals to 2, and we can just substitute Z, and we substitute the OH minus concentration in order to get the final answer. For question 3, we have iron is a transition metal in group A of the periodic table. Explain why iron has variable oxidation state. So the difference between 3D and 4S is very small. That's why they allowed them to have different charge number. For question Roman 2, complete the shorthand electronic configurations of Fe and Fe3+. So for Fe, it will be 3D, 6 and 4s2. And then for Fe3+, we will remove the 2 electrons from 4s and 1 electron from 3D. So that's why the 3D6 become 3D5. And for question B, an aqueous solution of iron nitrate contains the complex of FeH2O6 When solutions of KSCN and FeH2O6 are mixed, a color change is observed. The red complex FeH2O5 SCN2 forms. Define complex. So usually for complex ion, you can have the definitions in which a molecule with a central metal ion surrounded by one or more ligands. And then state the coordination number of Fe in FeH2O6 because you have 6 water molecules dative bonded to Fe, so it is 6. And then for the bond angles of water, it is 104.5. They ask you to suggest the bond angle of water. in the complex ion? Explain your answer. So when they form complex ion, the water molecule, basically they will use the lone pair of electron to form dative bond with Fe. So in this case, your water molecule, they will have 3 bond pair and 1 lone pair. So they will have 107 degree pyramids. And you can write the answers here. Lone pair from oxygen is donated in a bond. So you have 3 bond pair and 1 lone pair. The next question, explain why ion complexes are color. So first of all, you need to highlight that the degenerate d orbitals, they will split into 2 energy levels. And you need to mention the electron transition from low energy level to high energy level. And we also have absorptions of light energy in the visible region. Color seen is complementary to color absorbed. So all of these, they are the standard answer for why ion complexes are color. And for the next question, aqueous solutions of complex FeH2O63 plus and FeH2O5SCN2 plus are different color. Explain why these complexes are different color. So usually when you have different ligands, you will cause a different energy level or different energy change. So when you have a different energy change, you will have a different frequency of light absorbed, different complementary color seen. The next question, table 3.1 gives value for the stability constant of different complexes of iron. So this is FeH2O5, H2PO4 2 plus can form when H3PO4 react with FeH2O6 3 plus. Write an equation for this reaction. When this complex ion FeH2O6 3 plus react with H3PO4, this H3PO4 will become a bronzite lauric acid. They will donate a protons to one of the water to form H3O plus. And this H3PO4, they will become H2PO4 with negative 1 charge. So that's why the 3 plus will become 2 plus. And then for question Roman 2, write an expression for K step of FeH2O5 SCN2 plus and give its unit. So this is the equation for the ligand exchange. As you can see that this is FeH2O6 3 plus and they react with SCN minus to form FeH2O5 SCN with 2 positive charge. So when we write K step, we usually use product over reactant. This is the product and this is the reactant. Don't forget to have a bracket that close the charge as well because this is the concentration bracket. And we usually don't include water because water, the value is constant. So in this case, I will have my mole per dm cube for my product. And then this one will be mole per dm cube square. So the final unit will be mole negative 1 dm cube. For question Roman 3, use the stability constant in table 3.1 to calculate the value of the equilibrium constant Kc for the following equilibrium. As you can see that we have the FeH2O5, H2PO4 2 plus on the left hand side. So which means if let's say we refer to this half equation, this is on the product side and this is 5.9 times 10 to the power of 1. When the product change to reactant, basically we can just reverse it. While for this one is still in the product side for 1.3 times 10 to the power of 2. So this one is the same position. We no need to change it. And if you want to find the Kc for this equation, basically you just need to use the 1.3 times 10 to the power of 2 divide 5.9 times 10 to the power of 1 and you will get a 2.2. For question 4, ruthenium and osmium are transition metals below iron in group A of the periodic table. 2 different complex ions, X and Y, can form when anhydrous RuCl3 reacts with water under certain conditions. X and Y have octahedrogeometry. Aqueous samples of X and Y react separately with an excess of silver nitrate. Different amount of AgCl are precipitated. 1 mole of complex ion X produce 2 mole of AgCl. 1 mole of complex ion Y produce 1 mole of AgCl. Complete table 4.1 to suggest the formula of X and Y. If let's say this is 3 chloride ions, and then you form 2 moles of AgCl, it means that you have 2 chloride ions ionically bonded to the complex ion, and these chloride ion can react with your silver ions to form silver chloride. For the chlorine that attach to the central metal ion with dative bond, they cannot react with silver ions to form silver chloride. So in this case, we will be able to find the formula for X and also the formula for Y according to the number of mole of silver chloride formed. Question Roman 2. Both complexes react with an excess of bipyridine, BIPY, to form a mixture of 2 stereoisomers. Bipyridine is a bidentate ligand. Draw 3D diagrams of the 2 stereoisomers and use these to represent the ligands in your structure. So usually for bidentate ligands, we can have optical isomerism. So you can see that this bidentate ligand, you can flip the image to form the mirror image. Same goes to this and this. And the next question, they say that figure 4.1 shows another ruthenium complex. This complex contains the neutral ligands, suggests how pyrazine is able to bond to 2 separate ruthenium ions. Well, we have the lone pair of electrons on the nitrogen atoms. So for this lone pair of electrons, they can donate the lone pair of electrons to these Ru ions, and then they can form dative bond with it. For the next question, pyrazine is an aromatic compound. The bonding and structure of pyrazine is similar to that of benzene. Describe and explain the shape of pyrazine. In your answer include the hybridization of the nitrogen and carbon atoms, how orbital overlaps form pi bonds between the atoms in the ring. Okay, since it is similar to benzene, you need to know that for benzene, they are usually sp2 hybridization, because for every single carbons in the benzene ring, they are having the double bonds. So if this is sp2, then the shape will be trigonal planar. The angle will be 120 degree, and the carbon and nitrogen atom are sp2 hybridized with a p orbitals overlap sideways. Now we need to predict the number of peaks seen in the carbon-13 NMR spectrum of pyrazine. Explain your answer. So this is the pyrazine structure. I copy and paste. And then in order to find the carbon peaks, you need to find the carbon environment. So for all of these carbon, basically they are the same environment, because first of all of them attach to one hydrogen atom. And then the second thing, all of them have the same neighbor. So that's why we classified them as one carbon environment. For the next question, the overall charge of the ruthenium complex in figure 4.1 is 5+. Deduce the possible oxidation state of the 2 ruthenium ions in the complex. This is the complex ion. And then since the overall charge is 5+, and also this ligand is neutral, so it means that probably this Ru is positive 2 and this Ru is positive 3, but it also can be this Ru is positive 1 and this Ru is positive 4. As long as you give a whole number, oxidation number, and also when you add it up, it is 5 positive, then the answer is correct, but must be whole number. For question C, osmium tetroxide, OSO4, reacts with alkene in a similar manner to co-dilute acidified MnO4-. So this is your AS organic chem. When alkenes react with co-dilute KMnO4, they will give you DiO. So currently, figure 4.2 shows a proposed synthesis of a condensation polymer of G. And then this is SL chloride, and this is the DiO. And step 3, these two will form G. Okay, so for the first question, suggest a reagent for step 1. In order to change benzoic acid to SL chloride, we can use SOCl2 or PCl5 or PCl3. Draw the structure of exactly one repeat unit of the condensation polymer of G. The ester linkage should be shown fully displayed. So acyl chloride can react with phenol to form ester. You can see that we are having the C double bond O connected to the oxygens of this structure, and this one is one repeat unit. For question 5, compound Q can be synthesized from chlorobenzene in 7 steps using the route shown in figure 5.1. So for the first question, write an equation for the formations of electrophile for step 1. Okay, for step 1, we are having AlCl3 and CH3Cl. This is Friedel-Crafts alkylation. So for Friedel-Crafts alkylation, the CH3Cl, when they react with the catalyst, they will form AlCl4- and CH3+, and this CH3+ is the electrophile. For the next question, complete the mechanism in figure 5.2 for the step 1, the alkylations of chlorobenzene. Include all relevant curly arrows and charges. So, first one, I need to show the arrow from the delocalized system to the electrophile. After that, you need to change the delocalized system to partially delocalized, and then the electrophile is attached to this carbon. After that, the hydrogen, the bonding between carbon and the hydrogen, the electrons will be given to the partially delocalized system, and this one will restore, and the H will leave as a H+ ion. For step 2 is an oxidation reaction. Construct an equation for the reaction in step 2. Use oxygen to represent an atom of oxygen from an oxidizing agent. So for step 2, we are trying to change the CH3 into CHO. So in order to change CH3 to CHO, we need to have 2 oxygen, because one of the oxygen, they will react with the 2 hydrogens removed to form water, and the other oxygens, they will form the aldehyde. And then suggest reagent for the conversions of K to M in step 3 and step 4. For step 3, we are trying to change the aldehyde into hydroxynitrile. In order to change aldehyde to hydroxynitrile, this is your AS. You need HCN as the reagent and KCN as the catalyst. And then for step 4, you are trying to change the CN to COOH. So this is acid hydrolysis. And for acid hydrolysis, we need dilute acid or dilute H2SO4. For reactions that happens in step 5, I have CH3OH that react with the carboxylic acid to form ester. We call this as esterification, or you can call this as a condensations. For the next question, step 7 takes place when P is heated with a weak base such as K2CO3. So you can see that they are trying to let the Cl, okay, substituted by the nitrogen. Okay, so suggest why a strong base such as NaOH is not used for this reaction. We have an ester in P, so if you use a strong base such as NaOH, they will hydrolyze the ester. So if you want to maintain this structure, you need to use a weaker base. Q is optically active. Explain the meaning of optically active, which they can rotate the plane of polarized light. I know that some of the students, they like to write chiral carbon, but in A2, we prefer this answer rather than chiral carbon. So give 2 reasons why it might be desirable to synthesize a single optical isomer of Q for use as a drug. If let's say the enantiomers, they can rotate the light clockwise, for example, they can have a beta therapeutic effect. So if we synthesize it, then it means that we will have a higher yield of biologically active molecule, and we can use a lower dosage. Of course, you can write reducing side effects. This is also one of the answer. Yeah, so these are the reasons why it is better for us to synthesize a single optical isomer. Now for question B, Q is commonly used in conjunction with aspirin. Aspirin is a weak bronzite lauric acid. and the pKa is 3.49. 75 milligram of aspirin dissolved in water to form 100 cm³ of an aqueous solution. Calculate the pH of this solution. So since we are doing the calculation of a weak acid, first thing I need to find the concentration of the weak acid. I will use 75 milligram. I change to gram. I divide the mR. Then I divide the volume in order to find the concentration. And after I find the concentration, I will use this formula. H plus ion concentration equals to square root of Ka times the concentration of the weak acid in order to find the answer. So this is the concentration of H plus ion, and in order to find pH, we need to negative log. We negative log this answer and we get this. For the next question, aspirin undergoes acid hydrolysis in the stomach. Give the structure of the organic products of this acid hydrolysis. They have an ester linkage, so acid can break the ester bond. So when acid break the ester bond, you will get this one and this one. So means that this is the phenol that form after the breaking of ester bond, and this one is the carboxylic acid that is formed because of the bond breaking as well. Now we come to question 6. Amino acids are molecules that contain NH2 and COOH functional groups. Glycine is the simplest stable amino acid. The isoelectric point of glycine is 6.2. Define isoelectric point. So isoelectric point is a pH at which a molecule has no overall charge. And draw the structure of glycine at pH 4. Because pH 4 is considered acidic buffer for glycine, so in acidic buffer condition, the NH2, they will be NH3 plus, and then the COO minus will become COOH. Because when they form zwitter ion, this is the structure of it. So basically this one just maintain, and this one under acidic condition, they will receive the H plus ion to form COOH. Next question, figure 6.1 shows two syntheses starting with glycine. And then state the essential condition for reaction 1. For reaction 1, we are trying to let C2H5Br react with the NH2 in order to form secondary amine. Oh no, this one is a tertiary amine because the nitrogen is bonded to 3 carbons. So this is nucleophilic substitution. And for this to happen, you need ethanol as a solvent, and you need the condition heat in a soot tube. For reaction 2, we are trying to form an amide linkage. So for this amide linkage, this is the reagent that we use to react with glycine. So for this reagent, we need to have a C6H5, which is the benzene ring, and we need to have a COCl. Usually, acyl chloride is a preferable answer when it comes to the reactions to form amide. For the next question, draw the structure of the organic product U that forms when hippuric acid reacts with an excess of LiAlH4 in reaction 3. So hippuric acid is an amide. When you react with LiAlH4, kindly note that LiAlH4 is a strong reducing agent. They can change amide to amine. They can change carboxylic acid to alcohol. And the next one, we have a molecule of phenylalanine R can react with a molecule of glycine to form 2 dipeptide S and T. S and T are structural isomers. So in order to draw the 2 different dipeptide, it could be the case that the COOH is the one that react with the amine group. So we get this. Or it could be the case that the NH2 react with the COOH. So we are trying to show different possibility in this case. A student proposed a synthesis of hippuric acid by the reaction of benzamide and chloroethanoic acid the reaction does not work well because benzamide is a very weak base. Explain why amides are weaker base than amine. Usually for amides, the nitrogen lone pair is delocalized with C double bond O, or preferably, students like to say that this C double bond O is EWG. So they will make the lone pair of electrons of the nitrogen less available to accept H plus ion. For the pKa of chloroethanoic acid, it is 2.86. The pKa of ethanoic acid is 4.76. For pKa, the lower the pKa, the higher the acidity. Explain the difference between these two pKa value. Chloroethanoic acid is a stronger acid because of the chlorine, and chlorine is electron withdrawing group. And they have negative inductive effect, means that they will weaken the OH bond, and the H plus ion is easier to donate. For question D, compound V is another amino acid. The proton NMR spectrum of V shows hydrogen atom in 5 different environments as shown in figure 6.2. So in order to ease our comparison, I'm going to copy and paste. So, I already do it. So for this part, okay, first of all, for A, this is 9 to 13, and we get it from here. 9 to 13, they're representing the carboxylic acid. And because they don't have any neighboring hydrogen atom, so that's why it is a singlet. And then for B, this is the hydrogen that attached to benzene. So you can refer to the table, and then you can find the one that attached to the aromatic ring, which is this. Okay, and then after that for C, C is the alkyl group that attached to the benzene ring. So for 2.3 to 3, they're representing alkyl next to aromatic ring, which is pretty clear. And it is a triplet because they have a neighboring hydrogen atom, which is 2. And for D, this is 3.2 to 4.0 because they have an alkyl next to electronegative atom, and this electronegative atom is the nitrogen. Well, they are triplet as well because for the neighboring hydrogen atom, we consider C only. And the last one for E, this is the 1 to 5 because they are the hydrogen attached to the nitrogen. So this is a singlet because we consider N, and N doesn't have any other neighboring hydrogen atom. So usually for NH and OH, they will have a singlet. And complete table 6.3 by placing a tick to indicate any protons whose peaks are still present in the proton NMR spectrum of V taken in D2O. D2O is a solvent for proton exchange. They usually will exchange the proton with NH and OH. So in this case, this will exchange with deuterium. These will exchange with deuterium as well. And when they exchange with deuterium, they will disappear. The peak will disappear. So B, C, and D, the peak is still there. But A and E, the peak will disappear. And this is the end of our video. Thanks for watching this video, and I hope you enjoyed this video as well. Please click the like and subscribe button for more past year paper explaining video.